Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Colin Cherry, who's back to visit us again after a very successful internship several summers ago. But he's finishing up his PhD this time in the spring. And he's advised by Dekong Lin, who's been flying back and forth from Google to come and advise him. So we're happy to have you here today, Colin.
All right. Just let me get this one thing. What are options? Arrow. All right. Thank you very much for the kind introduction. I'm really super excited to be back here and seeing all these familiar faces and to be in front of you and get to talk a little bit about my work, which is going to be Inversion Transduction Grammar with linguistic constraints. But first, I come from the north to give you a brief lesson in perspective. I know you guys have had a rotten week lately, and you're not used to this, but this is me on my way to school. It's a 15-minute walk. That's so that I survive. And that's minus 18 Fahrenheit was the high on Tuesday. So I don't know if you knew it could go into the minuses, but it can. So the way this talk is going to go down is I have about 15 minutes of just brief introduction that is going to be, I think, review for a lot of people here, but just go over it, just make sure all our terminology is sound on Bitext, Bitext Parsing, SMT. Then talk about Inversion Transduction Grammar, or ITG, very briefly, and just lay out how that works. Then I'm going to talk about two projects that I worked on, ITG with linguistic constraints, and then softening up those hard constraints with a discriminative ITG where I've turned those constraints into features. In the very end, I'll close up and talk a little bit about some other projects that I've worked on, just touch on them in case you're curious about them. So, shouldn't really need a slide on statistical machine translation for this crowd, but just in case. The idea is that we have some source language coming in, a sentence in that language, and then another language coming out. So we want source language to target language. And the thing that makes it all statistical and mathematical is that we're actually going to be searching for an operation sequence that transforms our source language sentence into a well-formed target language sentence. And there's going to be all sorts of factors that go into that search, and you can search in many different ways. I won't talk about a lot of them here. But the thing that I'm interested in is that your weights on your individual operations are often determined by looking at data. You're looking at examples of translations to determine how much you like a particular transformation that a sentence can undergo on its voyage from English into French. So to do that, you're working with Bitext as the primary source of your examples. This is Bitext or parallel text. And this is, I think, well, it's an essential resource for training and testing statistical machine translation systems. And basically what you have here are large-scale examples of translation. So you get to see an entire document going from English into French. And if you, and it's actually fairly easy to drill down to the sentence level and actually find an entire sentence going from one language into another. But it does need some degree of analysis in order to determine the small-scale operations that are going to allow you to generalize to sentences you've never seen before. If you don't break the translation process down into smaller units, the best you're going to be able to do is look up sentences from your database that you've seen translated before and repeat them. So that leads me to word alignment, which is my favorite topic of my master's and PhD thesis, where basically given a sentence in its translation, you want to find the word-to-word connections. So here we have an English sentence and its translation taken from the Canadian parliamentary debates. It's translation in French. And you put that into a word alignment system, and what you expect to come out is some sort of linking structure here that indicates the translation relationships. For example, we see here that minister is translated into ministre, and vice versa. So throughout the talk, I'm going to refer to an alignment as a collection of links, where the links are a single word-to-word connection. And hopefully we'll be able to avoid the confusing terminology when I'm talking about one alignment between words. It should always be between sentences, where links will be between words. So, given a word alignment, you can do all sorts of cool stuff. You can extract the bilingual phrase pairs that are necessary to do phrasal SMT, which is kind of the de facto standard in how statistical machine translation is done. And if you add in a parse tree on the English side, you can do fun stuff. You can extract treelet pairs for dependency translation, as is done here. You can extract rules for a tree transducer, as is done at Kevin Knight's group at ISI. And then there's all sorts of other fun things you can do. And my current prime example is the idea of training a monolingual paraphraser, which there's been work done here and at Edinburgh that is pretty interesting. And it's driven with word alignment technology. So we're going to look at this in the context of Bitext parsing. There's a lot of ways you can approach word alignment, and normally it involves coming up with a story of how these two sentences came into being and how they're connected to each other. So the IBM models say one sentence began and then produced the other one, and the story of that production also tells you the alignments. We're not going to talk about that one right now. What we're going to talk about is Bitext parsing, where you assume a context-free grammar produced both sentences at the same time. So this is like a joint model, where you have both sentences springing into existence together. And it's like joint models in that you can watch the pairings as they're produced. That'll tell you your alignments. But we're also going to have this additional control, this additional machinery to talk about word position that's going to come in the form of syntax and grammar. And so it's going to give us another axis that we can play with in working on word alignments. So another quick review slide. To talk about Bitext parsing, I should first of all talk about monolingual parsing. So suppose someone came up to you at a party, as happened to me, and they start talking to you, and they look around a little shifty, and then they say, oh, you know him, he always, and they realize that someone's listening or something, and then they say, he always verbs the adjective noun. They just trail off, complete their sentence, but not say anything. So if someone says to you, he always verbs the adjective noun, the first thing you're maybe going to think is, what grammar produced this sentence? How could I build this with a CFG? Okay, so maybe it's not the first thing you think of, but yeah, you might get to it eventually. So basically, what you're looking for with a monolingual parser is to build a tree, and the tree is going to log the series of productions, where productions are just one symbol going to another series of symbols. And then the symbols can be classified as either non-terminals, which are our internal nodes of our tree, and terminals, which are our leaf nodes and indicate what you actually observed at the end of the day. So another way to view that process is someone started out at the beginning of the day with a big idea. I'm going to say an S. And then they kind of refined that until they actually had something to say. And so you start with a rule that brings an S into an NP and a VP, and you get something that looks like this. Then you apply another rule onto your VP, and you get something that looks like this, and you continue applying rules until you get your sentence. Now, the tree, you can see the tree reflected in this log, because that's the tree's job, is it just remembers the sequence of rules that you used. But this visualization is useful, because Bitext parsing is the exact same thing, but it happens in 2 dimensions instead of 1. So now we have 2 axes to deal with. One that describes our English sentence, and the beginning is at the bottom here, and moves toward the top. And then another that describes our French sentence, moving from left to right. And as we start out with our big idea, an S, we now have the option to say, well, as I break that down into an NP and a VP, I'm going to put the NP first in both my sentences. Then, as I break down the VP, I can say again that the verb is going to come first. And you can watch, no matter how I walk, I still say NP, V, NP, and again. So now as we're breaking down that verb, we have the option to say something interesting. Like we could say, for example, that the 2 languages are not going to agree in word order. As we walk in English, we're going to have NP, adverb, verb. And as we go in French, we're going to do NP, V, adverb. So the order is reversed in the other language. We can do something similar here, working in our top box. We can move and then do another one of those reversal operations. And then what I've done now is produced all the non-terminals in this tree, which is kind of hard to visualize in any way except this, where I have the logs of my operations here indicated by dotted lines. To produce the terminal nodes, all I have to do is place a symbol here on the right-hand side? Left-hand side for you guys. On the left-hand side for each box for English, and then on the bottom, that's the same for both of us, in French. And so what we get to is we travel along the English axis and we say, he always verbs the adjective noun. And along French, we say, il verbe toujours le nom adjectif. And I contend that this is at least as good French as this is good English, which is to say they're both not great. But it's a fun example. And if you want to recover the alignment from this, you can just see who shares a box. So verb and verb are both connected by the capital V. And so that is a link in our system. So why look at Bitext parsing at all? It has its problems. All these methods have advantages and disadvantages. I'll talk mostly about advantages here. The nice thing is you have a bunch of established polynomial algorithms, which are basically algorithms borrowed from the parsing world and extended into 2 dimensions. So we have algorithms for parsing and for sampling. We can actually reason about all possible alignments efficiently. And the framework is flexible. And by that I mean that it already has a lot of what I want to talk about encoded into it. There's already trees, there's already links. So if I want to do something like parse given an alignment, I don't need to look and ask, where do I put the tree? The tree's already there. And if I want to align given a parse, it's the same sort of thing. The other thing is that when working in a nice general framework like this, a lot of these parser-driven, Bitext parser-driven decoders look a lot like a Bitext parser aligner. And it's possible that discoveries that you make in one domain can be ported over easily to the other domain. So you can help decoding potentially, or you can steal ideas from people who are doing things in decoding. And at the same time, you're kind of plugged into that larger NLP problem because you're using the terminology parser and you're building parsers. So it's possible that you can borrow techniques from the parsing community, or maybe you could actually contribute something that they hadn't thought of before, but it's pretty well explored. So at this point, I've talked a little bit about Bitext and Bitext parsing. And now I want to talk very briefly about ITG, because all that is going to be is just the simplest possible Bitext parser. Actually, there are simpler. This is the simplest Bitext parsing formalism that Colin considers interesting. I think that's a safe statement. So this was introduced by Dekai Wu. And we have this idea where we have 2 operations extending CFG minimally so that you can converse about 2 languages. One operation is going to be this idea of transduction, where at your terminal productions, you have the ability to say something happens in one language and another thing happens in the other language. It outputs symbols to 2 streams at once, just like a finite state transducer would do. And that was represented graphically by this sort of phenomenon here. And then we have this inversion operator, which is what allows those what I referred to as deviations or reversals in word order before. Now I'll just use the term inversion. So every time I do a non-terminal production, I have the option to do a straight production, traveling up this way, so that I hit the non-terminals in the same order in both languages. Or I have an inverted production, where I hit them in the written order in English, but in the opposite order in French.
Are all productions binary?
Not just on this slide. In the Inversion Transduction Grammar formalism, you're capable of doing arbitrary size productions, but the only thing that's supported by the notation is this inversion operator. So if you have a node with 3 children, then you can only completely reverse them or leave them. So I guess my answer to your question is all productions aren't binary, but the system makes more sense when they are. You'd need a more expressive grammar to talk about the sort of reorderings you'd be interested in for a production with 3 children, for example. Does that help? All right. So that leads nicely into my next slide, where we're going to further restrict ourselves by making all productions binary, and by saying that we're only going to use one non-terminal. We're going to pick the letter A, because of tradition. So here we have A, and it's going to go to 2 A's in straight order, or in inverted order, or this little fella is going to stand in for every possible English-French word combination we could think of. And this is going to be our terminal production that's going to produce the words at the leaves of our tree. And so there's not going to be any linguistic meaning to A. There's not a lot of room for a lot of linguistic meaning here. But the nice thing about the whole package that we've laid out, and this is what people normally think of when they think of ITG. They think of ITG plus the one non-terminal binary bracketing grammar. The nice thing about that package, or one nice thing, is that you get a really neat visualization. So before I had to draw boxes and take up a whole slide with my example. Well, here I've still taken up the whole slide, but that's just because I made the picture really big. And what has happened is I've only allowed you to talk about 2 languages in terms of outputting different symbols at the terminal level. That means you only get to differentiate yourself between English and French at the leaf nodes of your tree. That means the tree is guaranteed to be isomorphic, modulo these reordering operations. So I can draw the same tree over both sentences. And then I can just indicate where these inversions have to happen with crossed bars here. And this is what you'll often see when you see an ITG described in a paper. And so what we have here is the Canadian agriculture industry, and we have 2 inversions working over this pair of constituents to allow us to do a complete reversal in word order and have it become Industrie agricole canadienne. So there's some pros and cons that come along with this bracketing grammar and just adopting this restrictive ITG formalism to begin with. We'll start with the pros because we're going to end up working in it, so might as well focus on the good things. The pros are that it's language independent. I can't possibly be intentionally favoring one language over another because I haven't put in anything. I just used the capital letter A. It doesn't mean anything. I'll just keep repeating this. That's all the points mean the same thing. A means nothing. So the second point is it's straightforward and fast to implement and fast to run. You've got a low grammar constant because there's only one non-terminal. And the symbols are minimally restrictive. This is kind of repeating the language independent idea. I'm never going to not build a particular portion of my tree because I don't like putting an A and an A together because that's all I got is A's. The cons are grammar is meaningless. I have syntax here. Here I have my big opportunity to say something about language and how humans communicate, and I'm choosing to say nothing. And because of the binary productions, we're going to run into something called the ITG constraint, which deserves its own slide. So the ITG constraint is just this idea, if you're using the ITG as an aligner, the result is that you cannot form particular link patterns. This link pattern, actually, which is called an inside-outside, and its reflection are both not allowed, where we have the outside here reaching in and the inside reaching out, and then the same thing happening on the other side. The reason you can't do this, you can't talk about this, is because if you try to plot the links in Bitext space, so each one of our links corresponds to a terminal in Bitext space, which corresponds to one of these boxes. If you try to plot them here, what you'll find is if you do a bottom-up parsing process, given these links, every time I try to, you'll have to imagine me drawing a little square around here. Every time I try to combine 2 symbols, this one and this one, I leave one out. I didn't get this guy, but I kind of used up that portion of space. So what's going to happen is the parser is just going to naturally never build these because it's never going to consider looking at them. There's no tree that corresponds to these leaf nodes. So it's just not going to happen. And for a long time, it was wondered whether or not this was a big deal and how often this sort of thing actually comes up in a real language. You know, people don't it's been suggested that people don't speak and translate in a way to violate these constraints. But ACL happened last year, and Ben Wellington did a very comprehensive study showing that it does happen. And even if you just scan, this is from Europarl, and I just scanned it using some Giza alignments and looked for, as a human, things that made sense and that I couldn't argue with. I couldn't explain away that some way that this was not the ITG's fault. And this was the best example I was able to come up with. 12 are acceptable to the commission, Mr. Burton, fully or in part, got translated into French with French words, but I'll just use the English here. Mr. Burton, 12 are acceptable fully or in part to this commission. It's actually more clear this way. I think the translator was trying to make things easier on the reader. And in doing so, you see this inside-outside structure happening. And so an ITG would not be able to model this. In all likelihood, it would drop the link between Mr. Burton, because that's the smallest loss. And that's not so bad, but it's bad. So there's your brief introduction to Bitext Parsing and Inversion Transduction Grammar as a tool for doing that. So at this point in the talk, you might be thinking two things. If you're not, hopefully you will be by the end of this slide. So the first thing you might be, those ITG constraints are kind of scary. You just showed us an example where they kick in and hurt you. And how bad are they? Well, probably what you're thinking is just throw away the whole thing and find something else. But I'm going to ask, how bad are they? And do they ever help? Are we ever glad, gee, I'm glad I held myself back that way? Or are we always kicking ourselves? And then the other thing is, here, I've been harping on that we just have this capital A. We've got no meaning behind our syntactic machinery. So you might be thinking, well, what if we added in some linguistics? What if you let me build you a grammar, or we tried to learn one, or we tried to do any number of smart things that involve linguistics? Well, let's stop and think for a second where that would eventually lead us. If say we tried to custom build a grammar. Well, we'd have some structural zeros probably in that grammar that define how symbols can fit together. That in turn would limit the trees we can build, which would limit the alignments that we'd end up producing. So what has really happened here on this slide is we're getting pulled in two directions. One part of me is saying, Colin, these ITG constraints, it's too much. ITGs are over-constrained, abandon ship. And the other side is saying, they're under-constrained. We have this option to be providing them with more information, and we're choosing not to. We could be providing more guidance here. So really, what I'm asking is, have I gone too far, or have I not gone too far enough? Or something like that. So what we're really talking about is this issue of alignment spaces, which is just this notion that whatever alignment method you're about to embrace to link up two sentences, you're going to have to talk at some point about the set of feasible alignments for any given sentence pair. What is the total set of alignments that I can produce? And this is normally described in terms of how links interact. And if links don't interact at all at some level, then the problem loses its structure. You might as well just be showing it two words with a bunch of features and asking whether or not this link happened, like a binary 0-1 decision. So you want...
That's how the Julian Lacoste aligner works, the original version.
Yeah. They think of it as adding in a discriminative, like a matching constraint.
Right.
Yeah, I was surprised when you mentioned that. Yeah, and actually, there's another aligner that works like that. I think I can't remember, but there's another group that literally just does an SVM classifier. And if you use your feature as the output of a whole bunch of other structured aligners, then it does really well, actually. So if you're designing a space, there's two things that you should keep in mind. You'd like to encourage competition between links, and I'll refer to this as guidance. You'd love for the space to come in and say, I know you'd really like to make this link over here, but if you want to keep all these other ones, then you can't. You'd like it to save you from making a wrong answer every now and again, kind of kick in and save you from some sort of model that's evaluating links. And it should not eliminate correct alignments. That's the other pressure. These are the two pressures I mentioned on the other slide too, right? Where you don't want to ever have the correct relationship between two sentences ruled out, as we saw in that Mr. Burton example. So the first space up for examination here is ITG space, where we're going to impose a one-to-one constraint on it as well. And we're basically going to say that it looks a lot like the one-to-one space, which I'll talk about in a slide, but we can't build these inside-out alignments. And what I'm often going to refer to that as is we can't reorder the English words in a particular way. There's a constraint on our way, on the reordering that can happen during translation. Our competitor in the less constrained portion of the arena is going to be permutation space, which is just the maximum matching algorithm. The only constraint we're going to enforce here, and this is just to make sure we have a completely level playing field, there's ways to extend each of these algorithms, again, because of Simon Lacoste-Julian in one case and because of Dekai Wu and others, to handle more words. Let's just keep it at one word right now just to keep things straightforward. And the nice thing is if we keep it one word, we get this sort of benefit where you can't use the twice, so it saves you from using this red link that you don't want to make. And it allows any permutation of concepts during translation, so there's nothing resembling an ITG constraint here. And the really nice thing is that it reduces to the weighted maximum matching problem so long as your model that's evaluating links evaluates them one at a time. And it can find the best alignment given a model for you in polynomial time, which is all you really need to do to have a comparison like this. Moving in the other direction, let's go grab some linguistics to constrain the ITG to see if there's any benefit from enforcing more constraints, providing more guidance to the system. There's a lot of ways you could have done this. And my method of choice, though, is to look at dependency trees because we happen to have a strong dependency parser at the University of Alberta. And there's a lot of things you can say about dependency trees, but the only one I'm going to talk about here is that they're trees that look like this, where the words are nodes and your arcs indicate some sense of linguistic modification or description. And the subtrees in your tree correspond to phrases. So here we have a subtree hanging off of board, and what we get is a phrase, the Canadian wheat board. Then we can appeal to this notion that if life were perfect, for me at least, then syntactic phrases in a tree would always stay together after translation. But instead, I'll just say they tend to stay together. In general, syntactic phrases tend to hang around each other after translation happens. And if we use this idea to constrain an alignment, we can expect to see some guidance because it's been shown that it'll improve alignment quality in the context of a beam search. So it should do the same for an ITG. So the way this works, forgetting the ITGs for a second, just the concept, how it can be beneficial, is that if you have a parse tree over top and we see a subphrase here like the tax, then what happens is if we want to rule out this link, we get our wish because this concept, the tax concept, has been pulled apart during translation and is now being interrupted by another concept from the English sentence, causes. So we can rule out this link even without a one-to-one violation. So we have another reordering constraint. We've limited how words can be reordered during translation. So now I have two very similar concepts. And we should just stop for a second and look at them and think about them before we start doing experiments, which will come soon. So I have this notion of an ITG, which forces alignments to be cohesive in some binary tree. So the thing is, I get to pick the tree. There has to be some binary tree where we're maintaining cohesion, but since I have a parser in the loop during the alignment process, it gets to be the most advantageous tree for building my alignment. On the other hand, the dependency constraints, I have to be cohesive in a provided dependency tree. So I've been given a tree, I'm stuck with it, like it or not. But I have to be cohesive, and that's what I have to maintain cohesion with. But the word that I left off here is binary. We've got an arbitrary parser handing us our dependency trees. No one said they had to be binary trees. So we're actually going to find that we get a little freedom out of that. And that means that the two spaces are not subspaces of each other. They have a more complicated relationship than that. You can't say one is subsumed by the other. For example, if I had the big red dog as my English sentence and I had a parse tree that looks like this for it, then I could build a non-ITG alignment and the dependency constraint would never complain. This is one big happy phrase, one big happy family. They can be resorted into whatever order you want. But the ITG would be upset as soon as you do an inside-outside alignment. At the same time, if I had a more restrictive dependency tree where all of a sudden I have a subphrase here, then it's easy to find the ITG can just roam a field and build whatever tree it wants. It's easy to find an alignment that will violate phrasal cohesion but isn't this and is valid to an ITG. Does that kind of make sense, everything up to this point?
So do you want to apply both constraints then?
That's exactly it. Yes. You guys are great. So, if we force the ITG to maintain phrasal cohesion with a provided dependency tree, then we'll effectively intersect the two spaces and only take alignments where both systems agree that it's a valid alignment. And what we've done without ever having to do anything in terms of grammar learning or grammar design is we've added some linguistics to this ITG alignment process. All of a sudden, it's benefiting from the linguistic knowledge inherent in your dependency parser. So, it's great to say that, but now I need to provide an intuition at least of how you actually do that. So, one way to do this is to look at your ITG, because that is where, let's assume we're working inside an ITG framework, first of all. The ITG is the more permissive space. It's what's going to be driving the alignment, and we'll maintain the intersection by checking with the dependency tree. So, what we're interested in doing is looking at all ITG trees. Let's forget the French sentence for a second. That could rotate tax away from the. So you see, if I built this little constituent here, I could place a bar here. I'm free to if I want. And I have now causes in between the and tax. Similarly, if I place a bar here, then I can rotate half the sentence in between the and tax. This is not what we want to be doing. If you look at enough of these examples, what you realize is that in order to generalize, the concept you really need to do is anytime you have a subtree, you can't have a span in English that starts inside that subtree, but then stretches outside of it without including the whole subtree. So we've left half of the subtree behind and gone and embraced the rest of the sentence. And that's where we get into trouble. So what we can do is what it's called a chart modification solution to this problem. We're using a chart parser to drive our alignment. So that just means that it has memoization or something to remember all of the constituents it's built. We can reach in before it's even started and say that any constituents that use either of these two spans, you've already checked those. They're negative infinity. Move along. You're not interested.
Nothing to see here.
Yeah, nothing to see here, exactly. So the effect on your parser is, here we are on our way to that alignment that I did not like. This is the one that I motivated my example with, where I have the aligning to the incorrect le. The parser is free to build this constituent. It's free to build that one. But in order to finish the job, it has to build this one. And it's going to look in the chart, and it's just not going to be there. So it's going to move on. And it's going to be forced to build something like this, where we have our two spans over here, just so you can keep track of them. These are the ones that we're not allowing. And the minute we decide, it doesn't actually matter where we place this box along the horizontal axis. The minute we decide to keep the and tax together, we've completely eliminated any ability for these constraints to affect us. And we can continue about our merry way, building the tree, and hopefully getting to the correct alignment, this time on the strength of some sort of model assessing link quality. So what I presented to you is kind of like a continuum of constraints, where we have the permutation on the left, closest to unconstrained. And then we have ITG somewhere in between. And we'll have what I'll call a DITG, which is an ITG with dependency constraints at the end. At least that's the way it should fall out. And turns out that's the way it does, just so you're not in suspense for the next two slides. So we're just going to race them. And we're going to race them by two criteria to find out which ones work best. We're going to work in English-French and use the 500 sentence label test set often maligned. It was not at the time at this of this research. So that's the best defense I have for that. And then we'll use our dependency parsers from Minipar. The first question I'm going to ask two. I'm going to measure both those axes that I said you should consider when building a space, guidance and expressiveness. So the first is going to be guidance. Does the space stop me from making incorrect alignments? And what I'm going to do is use the same weighted link score for all three spaces, and then just let a search go to town and find me the best alignments according to those scores in all three spaces. And the score is just going to be built just like you would if you were doing, say, competitive linking or something, where we're going to have bilingual correlations in between words, and then maybe a position-based tiebreaker. It's going to be very simple. And then what we're going to do is maximize the sum score of all the links in all our spaces and compare alignment error rate, which is a measure of combined precision and recall, where lower is better. So the results of the guidance test fall out mostly as I would hope to, actually exactly as I'd hope to. The least constrained space, permutation, maximum matching, is up here at 19, and it only gets better as we add in syntax, then linguistics. We add in the ITG, and we actually find out that we're getting a little leverage. I consider those ITG constraints very permissive from my perspective on this research. And it's actually dropping the error rate by 2 points. Adding in the dependency constraints on top of that, it's dropping it by another bunch down to 13. Won't try to do subtraction on the fly.
Did you just add in the dependency constraints on their own?
I did, yes. And actually, it's right here. Same line.
So the ITG constraints aren't adding anything to the dependency constraints?
No, but if you want to look at it the other way, they're not taking anything away either. Yeah, there is another slide with more results along those lines. So if we want to talk about expressiveness, this is this idea that given a strong model, we don't want the space to hold us back. So let's skip right to the strongest model. And we're going to go, and the model is the gold standard. It's going to just come in, and if I ask something to say, how much do you like this link? I could include it in my alignment, I could not. It'll say, I like it only if it's in the gold standard. Otherwise, it'll say, I hate it. Don't use it, ever. So
How did you deal with the possible links?
I just left them out at this stage.
So this is just the sure links.
Just the sure links in this data set, yes. So that is arguably a very sparse alignment for this data set. So the best space now becomes the completely unconstrained space. And we maximize our scores in all spaces, and now we check recall. Higher is better. And this will give us an idea if the space would hold us back. So what happens is the unconstrained is way up here, just to remind you that the model is perfect. By adding that one-to-one constraint, we immediately lose 4%. By adding the ITG, we lose very little. This is different now from other experiments you may have seen that measure it at the sentence level or something. This is just link level recall. We've lost 3 links by adding in the ITG constraints across 500 sentences. So at this point in time in the research, it actually looked like it was a minor loss to enforce these constraints. Then adding in the dependency constraints, we do see a noticeable drop. This is a whole % of achievable recall, and that can matter to you depending on how important it is that your system be able to recall all the links that are present in your sentence pair. So at this point in the talk, I presented a method to inject the ITG with linguistic constraints. I've shown that ITG constraints provide guidance, which I was kind of surprised by, with virtually no loss in expressiveness for this language pair, for this data set. And that the dependency cohesion constraints provide greater guidance, but we are giving up some expressiveness. So jumping right into the next project. At this point in the project, you may be thinking 2 things, or at least I hope you are after you've seen the slide. One is that the dependency cohesion does stop correct links, and we'd like to not have that. If we could have our cake and eat it too, we'd be happiest. So It stops them in cases like there's a parse error from the parser, or there's an extensive paraphrase, or an exception, a linguistic exception of some sort. So we'd like a soft constraint to handle those cases. The other thing is I consider myself a machine learning guy. And at this point, I haven't really said much other than appealing to a vague notion of bilingual correlation. I haven't said much about learning. So let's start doing some learning. It's the plan for this portion of the talk. So the soft constraint, the first point on the slide, is actually addressed fairly easily in theory, where we just say that those spans that I was reaching in and invalidating before, I don't need to just cross those out. I could just as easily just say, the parser, sure, you can use this span if you really want to. You just incur a penalty, say -5. And it's easy to incorporate that penalty into your dynamic programming algorithms, get a global solution to your alignment. The problem is, where did we get -5? Which brings us back to learning, which is nice, because that's the other point on my slide. It's what I wanted to look at anyway. So let's look at the state of ITG Learning in 2005 when I was looking at this problem. And what we mostly have is lots of great work coming out of Rochester. And it's EM to find the parameters for a stochastic grammar unsupervised. And it's driven by this incredibly cool but incredibly expensive two-dimensional inside-outside algorithm. And they're running EM on it. And at the end of the day, at the points of comparison that I have access to, they're not doing much better than I am with, say, phi-squared bilingual correlation. And they're doing a lot more. Computation time is devoted to it for about 1 point in error rate. I'm getting 17 with my ITG. They're at 16. So it's hard to get too excited. Meanwhile, I head off to Vancouver for EMNLP 2005, and the earth kind of just shifts a little as I have two people there up on stage, both telling me it's okay to use training data, it's okay to use arbitrary features. I have both Bob here and Ben Taskar, or I guess it was Simon, I imagine, on stage. You know, the playing field has been widened incredibly. Like, the sky's the limit. Arbitrary features, it was just blew my mind. So, and training data as well. It's nice to be able to show the algorithm when it's wrong. So I was kind of excited, and I wanted to get involved. So I'm pretty sure you're familiar with More 2005 here, probably. So let's just talk really briefly about the other solution that was presented at that conference, discriminative matching SVM approach. And I'm not going to talk a lot about it, but the basic idea at the core of things is we're still assessing links independently and then using a search to build up the best collection of links that fit together. The difference here is that instead of just having me say, oh, well, it's correlation with a phi-squared correlation with a position-based tiebreaker, you get to include phi-squared as a feature, and the position as a feature, and some morphology-based stuff as a feature, and an HMM approximation, and you can just include whatever you want. And then what the system is going to do is weight those features, add them up, and out is going to come your score for that link, how much the system likes the link. Max matching is going to find an alignment that maximizes the sum of the scores. So what we've actually hit here is a neat little case of linear algebra, though, where what we're allowed to talk about now is the features of an entire alignment. It's going to sum up these scores. So I could have just as easily summed up the features and multiplied the weights in at the very end. I'm free to do that if I want. And that means I can describe an entire alignment by a feature vector according to the features of the links in the alignment. Once I have terminology to talk about the features of an entire alignment as opposed to an individual link, then it's pretty straightforward to formulate what I would like an ideal machine learning process to do for me. I would like the weight vector multiplied by the feature vector of the correct alignment. So this is my correct score of my correct alignment to be bigger than the same figure for all the wrong ones. Seems pretty straightforward. I want the right answer to float to the top. Furthermore, I can incorporate this notion of structured distance if I'd like to, and say the wronger the answer is, the further it is away from the correct answer by some notion of distance, the larger this gap has to be. So once you have that notion, it's pretty straightforward to formulate it as a constrained optimization problem and actually just start doing large margin training. If you have access to a package like Cplex, it's actually fairly straightforward, assuming you can list all of these wrong answers. And that's where the solution falls apart. You can't list all the wrong answers in this case because there's an exponential number of them. That's why alignment is an interesting problem to look at in the first place. So there's a bunch of ways to approach this. An average perceptron is one. The discriminative matching solution is another. I went to do a third because this is research. I'd like to try something new. And because Thorsten Johims was visiting the department at the time, and he's kind of the champion for this method, SVM struct, and he does a really good job of selling it, and I had him right there to ask him how to work it. So the basic idea, again, I don't want to spend too much time on this, but is that you start with that big list of constraints that you wish you had, and you forget about all of them. And you empty the jar. And you just do the optimization problem with no constraints on matching your training set. That's going to give you a meaningless weight vector. You get your weight vector, and you search now in your first training example for the one of these that you are screwing up the most. The constraint where you want the correct answer to have a higher score than wrong answers. The case where the wrong answer was the worst in the other direction, so it's way higher than my right answer. I add that to my list of constraints, and I optimize again. Get a new weight vector, move on to my next training example, and ask again, what is my most violated constraint? I keep cycling through my training data and through this cycle until I eventually get this accumulated constraints get to the point where I actually converge. And you can prove that you're going to converge before you list that full exponential number of constraints that you wish you had in the first place. You'll converge in a polynomial number of iterations. So there's similarities here to the average perceptron. This is an online method driven by comparisons of your current output, your current system output, to the correct answer. But we have a few little bonuses. It allows this notion of structural distance, so I can say that some answers are more wrong than others. I return a max margin solution at every point, which is a nice guarantee for generalization. And the thing that really draws me to it is that little jar down here is basically remembering all of my past mistakes. So the system, I find, actually converges in fewer iterations, because every time it's doing this optimization step, it's doing it in the context of its entire experience of trying to generate the correct alignment for your training set. So I find it actually converges in fewer iterations, but the iterations are much more expensive because I have this quadratic optimization step in the middle. Of course, if your search is already kind of expensive because it's an ITG, then it's looking like a pretty good game. So at this point, we are free to build an SVM ITG, and it's actually fairly straightforward to do so with a package available online. Not that straightforward. It does involve a lot of code. You got to add in the search and the feature vectors and whatnot. But you give it all this stuff, and then the machine learning aspect of it just kicks in. And it will solve that optimization loop for you. So what we're going to do is we're going to parameterize the ITG, which basically means every production in it needs to have a score associated with it, some sort of weight, so the system knows the cost associated with using a production. Our link productions are going to be scored just like that discriminative matching system I alluded to. We're going to say A goes to causes followed by in one language and cause in the other. Well, just look at the link you're talking about there. Dig out all of its features, multiply them by the weight vector. That's going to be its score. So its feature vector is going to be identical to a maximum matching or discriminative matching solution. That's the same. The non-terminal productions, though, were kind of free to play. And so what I'm going to talk about, well, actually it's pretty straightforward. I hardly have to talk about it. What we're going to do is add only two features that are going to be active only for the non-terminal productions that look like this. And they're just going to ask two questions. Is it inverted? That allows me to uniquely identify whether it's this one or the inverted one over here. And does it cover a span that would usually be illegal? That gives it the hook in order to add in, by adjusting the weight of this feature, it allows it to give the penalty to that illegal span constraint that I had before. So I now have a soft penalty in place. Well, after the learner's finished, I will. So at this point, we're free to start experimenting. I'm going to, as closely as I can, replicate the setting of Taskar et al. In 2005. I have 100 training examples, 37 development. This is for setting SVM parameters and such. And 347 tests. We use the same unsupervised text as I was using before. I already have the infrastructure set up for working with this text. But it's only 50,000 sentences. There's no reason that this couldn't be 500,000 or whatever, a million, to develop my correlation metrics. This just was what I had on hand at the time. So let's go back now. Let's train it. The other thing I'm going to do, I should say, before I get to the graph, is I'm going to re-implement that system, the EMNLP05 system from Berkeley. I'm going to re-implement it using SVM struct and the max matching algorithm, and it's going to be my baseline. So the first thing to notice as we do the same experiment now, because what has happened is I have a representative now for permutation, but it's powered by the SVM because it's maximum matching. It's just like my previous experiments. It's a great fit. And I have a representative for the DITG space because I can just use this guy's parameters and shove them inside my my dependency constrained ITG, see how they do. So I can reproduce my experiments now with a stronger model. So I don't have the strongest model anymore. I just have a slightly stronger one.
Okay.
Yeah?
Are you going to eventually retrain the SVM weights, though?
Yes.
Right.
That'll be the next bar is missing over here. What we're going to find, though, is that the learning is a big win, first of all. We're already down to 11. Before, with all my syntax tricks and just using phi squared on its own, I was sitting at 13. So this is with no syntax, we're at 11. Adding in the hard constraints, we drop down to 10. And, I mean, any gain is good, but I'm used to seeing 30% drops from syntax. I'm used to this being the strongest feature in my system. And now I'm seeing this. I probably could have got this by just engineering my features a little bit better, too, or something. So this was a little disappointing. If we look at the reason that we're getting these results, we're seeing that I've inverted, by the way, precision and recall here, so lower is always better, just so you don't have to do the mental transform on the graph. You can see that we're making all our gains in precision, lower is better, and we're losing in recall. So the model actually didn't have to get that much better before we actually started running up against those constraints in expressiveness. We're seeing it now. There are links that we can't recall that the unconstrained system can. Moving on to, now if we push those constraints inside the ITG, or inside the SVM, and let it work with them, and know about them, and assign a feature to the constraint, rather than making it like a hard thing that it runs up against, then we continue to improve. This is now a 24% reduction with respect to our original unconstrained solution. We get middling gains in precision, nothing to write home about. The really cool thing is, all I set out to do was to get this lost recall back. And what has happened is I've gained that and then some. So what we're actually finding is this is a powerful movement feature. It's actually helping it recall links that a completely unconstrained system just couldn't find.
So the dependency grammar was already soft, wasn't it? Right. And so now this is the ITG constraint that's now.
No, it's the dependency constraint that's soft.
I see. So
nothing.
ITG.
This is unconstrained. This is the end point of the last section of research. So ITG and dependency together, both hard.
Right.
Yes. And this is, the ITG remains hard, and we're allowing the dependency to become soft.
Okay. All right.
So I was very excited to see this gain in recall. So the contributions for this section of the research is that we've seen a discriminative learning method for ITGs. And I've shown that the value of this hard dependency constraint is reduced in the presence of a strong learned link score. It's not worth nearly as much as it was back when I was playing with just bilingual correlation. But if we integrate that constraint as a feature during training, we can recover a lot of the power that we had before, and we can improve both our error rate and our recall. So at this point, I was just going to discuss very briefly just some other projects, so you know what else I've been up to while I've been gone. I was going to talk really briefly about applying some techniques from statistical machine translation to a new domain, so unsupervised pronoun resolution, and then a quick discussion on discriminative structured learning, because I really fell in love with this discriminative solution to word alignment, and so I wanted to play with it in another setting, so we'll talk about discriminative parsing a little bit. So really briefly again, Connell 2005, me and another one of De Conglin's students tackled unsupervised pronoun resolution. The president entered the arena with his family. What does his mean? Was it president? Was it arena? We'd like to build a system that can say president. And we'd like it to be able to handle more challenging examples than that. So the big idea here was you could formulate a generative model where a candidate generates the pronoun and the context and run EM using that model. Similar to IBM Model 1, if you look at it, if you think about it in the right way, it's like you have a pronoun at the bottom and a bunch of candidates at the top, and you're word aligning them. So there was a lot of cool stuff that had to happen to make this project actually work. We used linguistics to limit our candidate list. We used unambiguous, so that means binding theory kicked in, and whenever we knew there was a gender conflict, just because we could look up the gender of an object, we would just eliminate that item from the list. So basically our motto was never make EM guess when you know for sure. We used unambiguous cases to initialize EM. There's a subset of the data where there's only one item in the list for whatever reason. If you run the algorithm once with that and get it up and running with that kind of unambiguous data and then use that as your starting point for EM's local maximizer, then you get some leverage. And we also, at the end of the day, made a semi-supervised model by reweighting our component models discriminatively with maximum entropy. And the end result was we were able to come very close to supervised performance unsupervised, and we were able to match supervised performance with a far simpler generative model using this discriminative reweighting.
Was the maxent model completely unsupervised as well? Or?
No, that was using a development set. Yeah, so that's a semi-supervised.
So was that development set roughly the same size as?
Yeah, we used the same. We had an SVM to compare to right there that we were able to line up against, and so it was the same amount of training data, I think, for both systems.
Right.
Yeah.
So the main thing was you were exploiting the unlabeled data as well.
Yes. Yeah, we were exploiting the unlabeled data, and by doing that, we were able to match the performance of this highly engineered supervised system, even with just something that basically just memorized genders and common contexts for words. So the other thing I've looked at is discriminative dependency parsing. This is with the machine learning group at University of Alberta. And this is this idea, if we have a segmented Chinese string coming in, we want dependency parse tree to come out. The plan is to follow the template of McDonald et al. And have an SVM weight each potential link we could build in the parse tree, or arc in the parse tree, and then have a search, a parser, or a max spanning tree or something decide on the best links to include in building your tree. The big idea here was we were going to generalize without using part of speech tags. So instead of being able to use that sort of coarse representation to say all these words are all determiners and such, what we're doing is actually learning a completely lexicalized model. We're learning weights for every word pair seen in training and for word pairs that weren't seen in training, because they're going to be there in our test data. And we need to be able to evaluate well in that setting. And so to get that generalization, we leveraged the idea of semantic similarity that you can get by any number of methods. But you normally look at a bunch of words in context, build feature vectors from those contexts, get a similarity measure out. And then we actually altered the large margin portion of the SVM objective so that when two word pairs both involved similar words, we made their weights be similar. So you had to, the system was constrained so that similar pairs received similar weights. And that idea can actually carry you a long way toward generalization. And then we tried two constraint types as well. We tried this idea of local constraints, where you actually talk about individual links needing to score higher than other individual links in the system, versus another objective where you have entire trees faced off against entire trees. And it turned out that this, the local constraints, coupled with this idea of the modified objective, were able to actually get pretty good generalization without using part of speech. Worked on other stuff. Very proud to have been a part of the dependency treelet decoder developed here. And I've recently got my hands dirty with a little sequence tagging. This mostly comes from knowing how to work SVM struct and how structured learning works. All of a sudden, everyone around you doing sequence tagging sees your face becomes just a big SVM HMM. And you can help them out a fair amount, actually, by in all sorts of neat projects like biomedical term recognition, so pulling out the gene names, protein names from medical text. This is just a tagging task. I had a colleague that was actually solving it with an SVM, and we moved that SVM into a structured setting to improve results a fair amount. And then syllabification, we're finding syllable breaks in written words, and again, just tackling that as a tagging problem. So, introduced Bitext Parsing, ITG, went over the idea of using hard linguistic constraints in that setting, and then talked about how you could soften those hard constraints into features. And then I briefly discussed a few of my other projects, including parsing and pronoun resolution. So thank you very much for your attention. This has been great. Are there any questions? Oh, thanks. Go ahead.
So just two questions. One is, have you thought about making the ITG constraints soft and whether you think there'd be any value there? The second one is using dependency, presumably the dependency parser you used was for English.
Yes.
Do you think there'd be any additional information if you had a dependency parser for the other language as well? Yeah. And would you use it in just the same way, or do you think you could use the interaction of the two in some more interesting way?
Yeah, okay, those are two excellent questions. The first one, I have thought about making the ITG constraints soft. I'm not sure how much that would buy you. The big plan in this whole research, the way I was moving toward was actually trying to come up with an SVM that could match, not an SVM, an ITG that could match Giza in performance. And what I was looking for was all sorts of neat syntactic features, but I wanted to keep that ITG at its core because you get nice stuff like the efficient sampling algorithm. So I wasn't ready to give that up. But if I wanted to, and I wanted to move to, say, a beam search solution, as is done here, I think it actually would be fairly easy to include a feature that kicks in the minute your alignment that you're building violates ITG constraints. There is a linear time algorithm. ITG is horrendously expensive, n to the 6th to align with it. But there's a linear time algorithm to check to see if any alignment obeys the ITG constraint. So it would be practically free to just incorporate that into your beam search. I don't have a strong intuition about whether or not that would be a strong feature, but it would also not be a huge investment to check. The other thing that you asked was the dependency on the other side. The most straightforward way to do that would be you could now have three features. If it violates cohesion on one language, in the other language, and then some notion of shared cohesion. So anytime you use a span that is not agreed upon by both systems. Beyond that, I think you're looking at needing to get into more expressive tree-to-tree formalisms like Eisner's work on tree substitution grammars or something similar. But I wouldn't be surprised if those three features, if you did have a parse on both sides, bought you a lot, because having it on just the one side is worth a fair amount. So there should definitely be insight in looking at them both. Go ahead.
Have you looked at other language pairs? Because, and let me just add a little bit to the question, because the reason I'm asking is that these soft constraints, of course, have the really nice property that, you may make assumptions based, that work well for one language pair. If you go to another one, you can adjust the weights so that certain restrictions become less powerful. So it seems actually that this would be, a good candidate to test across different language pairs and
I agree, and unfortunately I haven't, and I have no good reason other than time constraints. Yeah.
Okay.
I do think that would be really interesting. I'd love to see again how the value of that constraint goes up and down as you move to other language pairs. Now that I'm thinking about the double tree idea, I'd love to try that too. Actually, there'd be.
That you could add. Sort of known linguistically based constraints, and just have the system learn the weights of those.
Yeah.
As long as they are computable in a reasonable way.
Yeah, no, definitely. And you can definitely do stuff along these lines. For example, with the system right now, it's only obeying the phrase structure of the dependency tree, and it's not paying any attention to the head structure. And the head structure actually imposes additional constraints. And that's why other people have written papers talking about how dependencies aren't as great a representation as everyone thought they were for translation. And it turns out that whether or not you agree with that statement largely depends on whether or not you're insisting on maintaining head structure.
Which way does it go?
This one...
If you maintain head structure, are things better or worse?
It gets only slightly better as a hard constraint. I haven't explored it as a soft one. It only gets slightly better as a hard constraint, and you get... Just a second. Skipped a few too many slides. The HD ITG was in this talk when I found out that the talk was 2 hours long. So it got cut, but it's the one with the head constraints. And you'll find that actually what it maintains is distance to head, which is not something you always want. Canadian wheat board actually moves the wheat further away than Canadian from board. And to do that, you have to build this tree, this ITG, that looks like this, where you kind of invert Canadian and wheat, and then, or you don't invert Canadian wheat and then rotate the whole thing. And so what happens is that, I don't think this tree is right, but the idea is you do have to build something like this. And it doesn't agree with the dependency tree. What we're saying is that board was modified by wheat and Canadian independently. And this ITG is saying that board was modified by a joint modifier that includes both Canadian and wheat. So you lose the ability to express this, and that alignment drops out. So you actually get a fairly large expressiveness hit for almost no gain in accuracy. But as a soft feature, why not? And that was on my list. Like while I was working on this, it was right there, and it just fell off, unfortunately. So I didn't get a chance to look at that.
Did you do any experiments plugging the alignments into a system to see if in addition to improving alignment error rate, they actually improved translations?
I'm working on that sort of thing right now, actually, at this current phase in my thesis. And right now, I don't have very high hopes. I would have higher hopes if I was plugging it into something like a tree transducer or the treelet system here, that this would make a big difference. But in terms of just plugging it into Pharo, I haven't seen anything so far. No. Any other questions?
Have you run Giza as a baseline on the same data set?
Giza, yeah, this data set Giza can get down to 5 using intersection, as can I if I take the gloves off and use a beam search and the dependency constraint and a bunch of other things. This was more just an exploratory, how does ITG relate to everything? How do these things all interact with each other? It was more of that sort of study than a strict attempt to win on this data set, which is getting harder and harder every year, thanks to some people in this room. Okay.
Do you think that some of those sentences for which the alignment violates the constraints may actually be bad translations, and then it could be a way to remove them?
For the ITG constraint, I've done I would call it a pilot study, but a less generous term might be I've looked at the data for an hour or two. And it does look that you can use ITG violations using like so I alluded to this when I gave my example. I said I've gone through Europarl, I've aligned it with a very high accuracy but sparse aligner and looked for good examples of non-ITG. And what I get are a lot of examples of translations where the translator has actually inadvertently changed the meaning in how they've reordered things. But of course, I do get other examples like the Mr. Burton one. So you could use a series of things like this actually to try to weed out incorrect translations. I don't have any empirical intuitions. I don't know how many you'd be able to detect, like what your precision or recall would be. Certainly your precision would be low. There would be lots of false positives where the constraints, where there's another problem with the constraint. Either the linguistics is flawed or the parser has made a mistake. But if you came up with some way to post-process, like use that as an initial run, and then found some other way to separate the true incorrect translations from the false ones, you might be onto something with that sort of approach.
Well, just looking at that, so this is a case of I'm about to try and generalize from the one example that you have. So take this with
Utilizing your training as a linguist.
That's right, exactly. Yeah, utilizing my linguistic background. Yeah. Speaking as a linguist, right? Yeah. Maybe what was going on there is that the English was actually spoken, and so I think you get to see lots of things like the sorts of heavy NP shift, and then the French was actually produced by a translator who was then cleaning it up, right?
Yes.
But I mean, if you were translating from English into French, you'd actually have to work with the English that you were given.
Right.
Not the English that you want. That's right.
Maybe
that's what we should be looking at.
Right. And there must be a bunch of things like post relevant clauses and things of that sort. That would trigger that kind of.
Yeah. Dekai is the person to talk to about stuff like that. He has a whole wish list of things he'd like to cross out from the English language, I think. But yeah, I agree that we're definitely running into problems with spoken text here, because stuff like putting that Mr. Burton in the middle is not necessarily what you would do if you were sitting down and composing this.
So one thing that I kept thinking that you would get to eventually, so in the ITG framework and in what you're doing, is there any place for many to one-to-many links at all?
Yes. Yeah, there is, for sure. How can I do this with only the materials granted me here? What I can do is go back to my big graph.
There's a whiteboard behind you.
There is a whiteboard, but I hate drawing these big squares. So I'm going to just try it with this, and we'll go to the whiteboard if that doesn't work. So we have this, pretend these were meaningless or something. We have the option at this phase during parsing to just say stop. And if we stop anywhere here, and then we were to label these with terminals, we get something where we get, what was this? The adjective noun goes to le nom adjectif. And you can get sort of phrasal relationships. And that's what I've been trying to leverage lately, is instead of saying, oh, it was one slide forward instead. Instead of saying that this is my grammar, with these being my terminals, I change those terminals here, EF, to be arbitrary sequences. And what the grammar ends up looking like, we will go to a whiteboard for a second, is this is roughly it. But A has an option to go to AA. Well, basically, you add another production that's a C. AA, and then a C. And this guy kind of becomes your probability of stopping and generating some phrase. And this can be the whole sentence, or it can be just a few word pairs, like a complete many-to-many representation. I was so excited when I realized this that I kind of thought I would take over the whole field of joint phrasal alignment. Turns out, because in this setting, an ITG has all the advantages. This basically becomes a big joint model. Your C parameter just remembers all the various word pairs, and they all share probability mass. So it's a big joint model, just like Marku and Wong, 2002, or the recent work out of Edinburgh. And we would get perfect search and perfect counting algorithms from the ITG. But it turns out that those two things don't buy you a whole lot, and just the search people are currently doing and the counting algorithms people are currently doing. If you're just looking at the impact you have after you throw these phrase pairs into Pharo, I think the flaw is in EM, and it's not in the search and the counting. It's somewhere deeper. It's in with this how certain EM gets. That's not necessarily an answer to your question. What was that?
No, I was wondering whether the flaw related to the paper by John Donato and NACL.
I don't think is that one from Berkeley?
Yes.
Yeah, I don't think that's it either. I think they sidestepped the flaw there by looking at conditional models and introduced a whole new set of flaws, so that they were having like a phrase given a phrase, and that was where you got this whole ability to hide data, basically in obscure partitionings. You could be incredibly.
That EM like to pick the most perverse partitioning possible to give you the sparsest data, so you could concentrate all your probability mass on the rare things that you saw.
Exactly.
And avoided looking at the common things.
Yeah. So the thing that avoids that with joint models is that your entire mass is shared. So there's no advantage for the system to just to assign mass to sparse events. It's benefited by assigning them to common events. But the joint model has all sorts of other problems. Primary among them is its favorite alignment is this whole sentence goes to that whole sentence. And that's a hard one to break. And there's a bunch of ways to fix that, but it's not clear if any of them are right. And even if you do fix it, EM is much more certain than the current surface heuristics for extracting phrases for Pharo. The heuristics for extracting phrases for Pharo are designed to never guess when they don't know. They always just count everything once, right? While EM will often guess when it has no real reason to guess one way or the other. It just prefers to be certain because it's climbing in probability space. So that's been my experience with that. What I'd like to explore coming up is more sort of discriminative solutions with this sort of representational power. I'd like to go back and show it training data. Have it say, have me say to it, this is what a good alignment looks like. Now reproduce that, rather than giving it to EM and hoping that the right alignment comes out at the end of the day. All right, that's fantastic. Thank you.